Yo, what's up, guys? So today I'm going to teach you how to solve electrochemistry problems using my table that I designed. As you can see, the table is very simple. You can actually reproduce this anytime in the exam, and you are assured that 95% of the answers that you need under electrochemistry, you'll be able to answer them using this table. So the first thing, I'm going to explain the table, and then after explaining the table, then I'll move on to actually giving you an example of how you can apply the table in the exam. Right, okay, so the first thing that you're going to write is E and G, and E represents the electrolytic cell, and then you can guess G obviously represents the galvanic cell. And then under E and G, you can see we've got positive and negative, and the way that you can remember this is in order, right? In math, usually if you're doing math, you know that when you're writing the two signs on a number, you usually write plus or minus. So you start with plus and then minus. So it's the same thing, is going to be EG or EG plus or minus. That's how you can remember this. Now let's look at this information here. On this information here, you can see that A is representing the anode and O is representing oxidation. And now moving on to the other side, you can actually see that in an electrolytic cell, the anode is going to be positive, and in a galvanic cell, the anode is going to be negative. So like I said, we're going to be using this example of copper and silver. So sometimes in the exam, you're going to be asked to actually write the half reactions in this galvanic cell, and you're going to be provided with a table of reduction potentials, and that's the one that you're actually going to use. So let me just go to the tables. Right, so I'm going to look for silver, and as you can see here, this is my silver information, and then I'm going to look for copper. You can see there is this copper here, there is this copper here, and let's see, there is this copper here. So which copper are we going to use here? For silver, it's straightforward. As we can see, there is only one silver here, but then for copper, we've got a variety of them. So now, what you should just know is, number one, the half reaction that you're going to choose must be the one where the ions are going to be reduced to solid state. That's the first thing, unless otherwise the question have stated something. And also, you must know, most of the times we are going to be using the +2 oxidation state. In other words, reduction from +2 to solid, unless otherwise also there are some substances that have got +1, like silver here. You cannot have a +2 on a silver atom. So that simply means that we are going to choose this one here, and of course this value here. So for silver, the reduction potential is +0.8, and then for copper is +3.4. So I'm going to go back and write the information. Right, so for copper, it was copper 2 plus 2 electrons. This was giving us copper, and then the reduction potentials was 0.38 volts. And then for silver, it's a G plus an electron to give a G, and the E cell was plus 0.80 volts. So using the table here, the information that we can get straight up, all right, is that number one, this cell here is a galvanic cell, right, or voltaic cell. So since it's a galvanic cell or voltaic cell, that simply means that the information that we are going to be using is here. So in other words, straight up, we can actually say the anode is going to be negative, and at the anode, that's where oxidation is going to take place, and then of course the cathode is going to be positive, and reduction is going to take place there. And you can see this is coming from the fact that if the anode is going to undergo oxidation, then automatically the cathode is going to undergo reduction. And also, if the anode is negative, then the cathode automatically becomes positive. Right. Okay, so this information we get straight up from knowing that it's a voltaic cell hence the anode is negative, and oxidation takes place at the anode, and the cathode is positive, and reduction takes place at the cathode. That's the information that we have here. Now, let's go to our half cells. So on our half cells, we have to decide which one is going to undergo oxidation, which one is going to undergo reduction. So there are two ways to doing this. So the first way that you can actually decide on which one is going to undergo oxidation or reduction is by using the table. Okay, right. So the way that you're going to do it is looking at this is our silver and looking at our copper is here. What you're going to do is first you're going to use this part here or this part, but you can use one side only, right? So now, as you can see, they're saying increasing reducing ability, which means as we go down, the reducing strength of the substance increases, which means up there will be weak reducing agents, down there will be strong reducing agents. In other words, these are weak reducing agents, and these ones are strong reducing agents. So now, armed with this information, you'll be able to appreciate that since copper is at the bottom or is below the silver in this case, or it have a stronger reducing ability, then that means it's going to actually reduce the silver. And at the same time, as it reduces silver, it's going to lose electrons and hence is going to be oxidized. So in other words, what we're simply saying is copper is going to reduce silver, and then silver is going to be oxidizing copper. In other words, our half reactions are going to be like this: Ag plus an electron to give us Ag solid. And then for copper, it's going to be copper give us copper 2 plus 2 electrons. As you can see, silver here is undergoing a reduction, and then copper here is undergoing oxidation. So in other words, also the way that you could think of it is, if this is quite confusing to you, the way that you could think of is that the one at the bottom here is going to undergo oxidation and the one on the top is going to undergo reduction. Now, the second way that you can also think of it is by using these E cell values. So those cell potential values, what they're going to do is they're going to show you that a substance that is more positive is going to be able to get electrons from a substance that is less positive. So like we said, silver is going to undergo reduction. So that means it's going to be the cathode. Hence, it's going to be Ag plus an electron to give us Ag, which is a reduction. And then automatically copper is going to undergo oxidation, which is copper to give us copper 2 plus 2 electrons. So now this information is going to help you to solve all the problems that you're going to be dealing with. For example, if ever they say that they want you to write the net equation, that means what you're simply going to do is going to add these two equations, this one and this one. However, you must take note that the number of electrons in both equations are going to be equal. So since we have 2 here, we have to make this one 2. So to balance the equation, we multiply by 2 here and 2 there and 2 there, and then we add the 2 equations. And then when we're adding the 2, let me just rewrite them. Right, so whenever we are adding this 2, what we're simply going to do is we're simply going to add just like this through the arrow. It's going to be copper plus 2 Ag plus the 2 electrons. 2 electrons, these are going to cancel out, give us copper 2 plus copper right there. So this will be our net equation, and it's balanced as it is there. Now let's move on to the cell notation. So for the cell notation, the first thing that you have to know is that a single vertical line like this is going to represent a phase change, and a double line is going to represent a salt bridge. That's all. Now, let's write the cell notation for this galvanic cell. You always start with the anode and then the cathode. So the anodic reaction, or the reaction that takes place at the anode, is copper solid, and it's a different phase to copper 2 plus aqueous, and they're separated by a salt bridge. And then the cathodic reaction is Ag plus in aqueous separated by phase a line to give us Ag solid. This will be our cell notation. Now let's move on to calculations of E cell. So E cell is equal to E cathode minus E anode, or E reduction. As you can see, the cathode undergoes reduction, and E anode, or E oxidation, same thing. So this will be equal to E cathode. Our cathode, as you can see here, our cathode is silver, and silver is plus 0.80 volts, minus E anode. Our anode is copper. Copper is 0.38 volts, and it's positive 2. This will give us positive 0.42 volts as our final answer.